And so what we're going to do is today, I want to just show you, it's not necessarily a super great demonstration, but it does illustrate a couple of key points here. And I'm going to share my screen. The first idea, and you might want to have some paper, something to write with here as we're going through this. Let me go ahead and change that over. Okay, so and if you don't mind here, Carter, can you give me a heads up here? Are you seeing white paper there that I'm about to write on?
Yes.
Okay, brilliant. So let's do this. One thing that we sort of blew right past and just didn't have time to talk about is something called Dalton's law of partial pressure. And I think it was Alex yesterday, we talked about this one, and this is really not super scary at all once you kind of get into it. Let's say that I have a container, and that container contains three gases. One of the gases is represented by X's. Let's say that the X's represent hydrogen, H2 molecules. Let's say that there's another gas in here, all right? And let's say that the dots represent O2. And I'll even throw a third one in there. I'll do some little squares, and let's call that helium. Now, as I put more and more gas in here, and Carter, since I know your sound is super awesome, I'm coming to you. As I put more and more gas in here, what's happening to the crowdedness in that container?
It's becoming more crowded.
Becoming more crowded. So what do you think is happening to the amount of pressure as you keep putting more and more gas into the container?
Pressure's going up.
Probably going up. So that's a pretty good idea. So if we just say, listen, let's say that the pressure from the hydrogen, the H2, is equal to, I'll make it easy numbers, 1 atmosphere. And let's say we put enough molecules in for the O2 to give us 2 atmospheres worth of pressure from the oxygen. And then we go over here and we put in maybe only half an atmosphere worth. All right, so we put in just enough of molecules of gas at that particular temperature for that particular volume to create that pressure. Carter, I'm gonna see if you can knock this out of the park. If these are the pressures for the three things individually, what do you think the pressure in the container is total?
Do you just add them all together? Or
Bingo. There is nothing super
three and a
sneaky
half?
about this.
Three and a
You
half?
literally, you literally add them together. So I'm going to take the pressure from the hydrogen plus the pressure from the oxygen plus the pressure from the helium, which would be 1 plus 2 plus zero point 0.5, just leaving off units, but I'll put them at the end. And so Dalton's law of partial pressure is literally this easy. You just add the pressures, okay?
Isn't it 3.5?
Because I'm not properly caffeinated because I only drink decaf coffee now. You're exactly right, Lauren. Thank you. So if I wanted to write Dalton's law of partial pressure, if we ever want to find the total pressure in a container that contains multiple gases, you're going to just sum up the pressures of all the gases present. So you could have more than 3 gases in the container. So that one I wanted to start pretty easy. You guys okay with that idea?
Yes.
Okay. If you got a question there, ask it, but I'm gonna go ahead and scooch this down a little bit. Now the next part involves using this Dalton's law of partial pressure. And the reality is when we do experiments with gases, oftentimes gases are hard to collect. Sorry about that beeping noise. Let me turn off my email. So when we collect a gas, sometimes we have to collect it over water. And now I'm going to sort of shift my camera a little bit and see if I can get this to work. This is definitely low budget. Mr. Caldwell doing some finagling of stuff in the kitchen. All right, Lauren, do you see the little container of water there?
Yeah, I do.
All right, to make the water a little bit easier to see, I'm just going to put some blue food coloring in it because with the camera, it's a little bit tricky. I'm going to stir it up Get a nice little blue color in there. And you may have done this when you were a kid playing in the bathtub. You got your little bathtub toy and you got a little cup. And, so I've got the blue liquid in there. And you fill the cup up and you invert it. And lo and behold, can you guys see how the blue liquid is still in the cup there? It's a little bit hard to see. Bloop, it just popped out. So what I'm going to do is I'm going to imagine, let's see if I can get this a little bit further away so you guys can see it better. So I've got blue liquid in the cup. The reason that that blue liquid is there is because air pressure is pushing down on the surface of the liquid here, right? And air pressure is 14.7 pounds per square inch. It's 101.3 kilopascals. It's a certain amount of push. Now that's pushing down, and it's actually holding up the water that's trapped inside the upside down plastic cup. Now, if I do a reaction, let's say I was doing a reaction directly underneath this plastic cup. I'm sorry for the funny angle, but I'm trying to do a lot of things here with only two hands. Let's say that I had a reaction. Now, I don't have any chemicals here at the house that were handy. My baking soda is all gone and vinegar is used for cooking. But what I'm going to do is just introduce a little bit of gas bubbles here. Whoop, too many. Let me try that one more time. One tiny little gas bubble. Right, I'm hopeful that you guys can make out. Lauren, can you see that now there's a little bit of liquid still in the cup, but
Yeah,
there's
we
now
can.
some bubbles? Okay.
Yeah.
So here's the thing. Let's imagine that that was an actual chemical reaction instead of me just blowing air into the straw. We've now collected our gas over water, all right? And so I'm going to go ahead and shift gears and draw this so that this can hopefully make a little bit more sense when you encounter a problem that says a gas collected over water, which is what you had in problem numbers, I want to say number 5 especially. I went ahead and in the solutions that I gave you on the Canvas course, I said, let's just omit problem number 6 because, gosh, it's just hard doing this stuff online. So here we go. If I collect the gas over water, what you've got to realize, I'm going to draw this, is that even though right now I'm sitting at room temperature, right, there is water that is turning into the gaseous state, the most energetic particles, right? So the water level is right here, water level is right here, and the water level is right here. So inside of this is gas. And so what it's actually a combination, all right? This gas is going to be having a little bit of water vapor in there because water vapor is always evaporating. Now, Chris Short, I'm going to come to you here for a second. What's the temperature at which water boils? Oh, I put you on the spot, or maybe I lost you. Chris, can you hear us? All right, no big deal. Water boils at 100 degrees Celsius. And so what we have to understand is that inside of this, there's a total pressure. And that total pressure is going to be made up of some of the pressure is caused by the gas that we were actually trying to collect. But then the rest of the pressure is caused by the little bit of water vapor that is happened to be trapped in here as well by nature of the fact that at any temperature really between 0 and 100, we should expect some small amount of water vapor to be stuck up in here. Now, how much pressure is going to be attributed to the water vapor? That's going to depend on the temperature. I'm going to pull this chart over from the worksheet. And you'll notice that as the temperature goes up, that pressure that the water contributes goes up as well because the warmer water has more energy, so more particles can jump up into the gaseous state. And this is all tricky stuff, guys. This is the most confusing part of this unit, I think. So at the end of the day, what you have to realize is that you have to, if you're given a pressure value, you have to recognize that that's a total pressure if it's collected over water. And you have to write this expression. If you actually want to find the pressure of just the gas you're interested in, you have to subtract out the pressure of the water. And what I thought I would do here is kind of pull over the question and the answer for number 4 and 5, because that was the stuff that was the most difficult on the assignment. Let me go ahead and move this. Okay. So question number 4 and question number 5, I hope that these are now going to be pretty easy for you guys. So we've got 3 different pressures in problem number 4. And so if I want to know the total pressure in the container, you literally just add them. And then when we look at question number 5, it's asking you to, hey, you collected a gas and it gave you these values, volume, a temperature, and a pressure. So in part A, we went ahead and said, hey, okay, if the pressure is 700 millimeters of mercury, and I want to know the pressure of the gas, I've got to subtract out this 12 millimeters of mercury, understand where that comes from. This is at 14 degrees Celsius for part A. So if it's 14 degrees Celsius, the partial pressure is 12. So that's where that number comes from. And I think that's what makes these the sort of the trickiest problems on the page. So that's where I get this 12 from. And honestly, if you understand this, that's amazing. If you don't understand it, you're going to be okay too. It's not like you're going to suffer greatly in life. But I did want to just kind of go over that with you guys. And I'm going to pause for a second because that was a lot of me talking. Any questions you want to ask? I want to do one example problem with you, and then we're going to call it a day.
Okay, so for 5A, I'm confused why you have like I thought it was just like the P total equals the gas plus the H2O. Why do you have V1 T1, and is there another equation that goes into effect there?
Okay, so the first part of it was, as we look at the problem, we just wrap our minds around the fact that, okay, I've got a volume, I've got a temperature. You're okay getting this 688 pressure number?
I'm confused how you get it. Like I'm a little like
Okay.
I get how you get the 12. I just don't know where to go from there.
Okay. All right. So let me just take a step back. It said that the pressure of the gas that we collected was 700 millimeters of mercury. And because it was collected over water, I have to remember that that pressure, that 700 millimeters of mercury, is a combination of the pressure of the gas that I'm actually interested in, plus the pressure from the water vapor. So that's where I had to do a little bit of thinking to get to the actual pressure of the gas I'm interested in. Okay. So that's kind of like step 1. And then you reread the problem and it says, we want to know what would the volume of this gas be if it was dry, which means, okay, we've gotten rid of the water. We're dealing only with the gas itself. And it was at standard pressure and standard temperature. So this becomes one of those problems where you have, the initial values and the final values, because standard temperature is this, which is definitely different than the previous one. And standard pressure is this, which is definitely different than the previous one. So instead of it being just one set of values, which would then have kicked it over into the, excuse the movement, PV equals nRT, it gave you 2 sets of values. And that's where you go, and the combined gas law is super useful there when you have initials and finals. So Alex, these are hard problems. Is that a little bit better for you?
Yeah, it's a little bit.
Okay. And like I said, if this is still just kind of muddled and confusing, it's going to be okay. All right. But it's a good question. And, I can walk through these, and still a decent percentage of students still struggle with this stuff because there's a lot to think about. Anything else before I do one quick example and then we call it a day? Okay. So let's do this. And it's going to be similar to sort of the ones that I gave you there. So let's go ahead and say that, get rid of that water stain. All right. I'm going to find my hand. There we go. Example. All right, let's go ahead and say that a 400 milliliter sample of gas is collected at 20 degrees Celsius. The pressure in the container is 700 kilopascals. And then we're going to say what would the volume of the gas be at STP. And so as you sit there and you're like, I don't even know what to do. First thing to maybe think about is, does this seem like a problem that has one set of conditions or two sets of conditions, a before and an after? Anyone want to take a stab at that? Is this a one set or a two set type of problem? Nobody wants to venture a guess. I hear it. Someone, go ahead.
Two set.
Because one of the values is at STP, and the other one is at clearly different temperatures and pressures. So very nicely done, Stella. So in the back of your mind, you should be thinking, at some point, I probably want to use this equation. So we'll just write it to remind ourselves. And then we'll start sort of organizing our thinking. So the 400 milliliters appears to be a volume. We've got a temperature of 20 degrees Celsius. We never work in Celsius. We convert it to Kelvin. And if I make a mistake anywhere along here, please pipe in because I'm uncaffeinated. Don't know anything about the number of moles, but I do know that the pressure, and this is where we have to be super careful. If it is collected, and did I say that it was collected over water? I did not. I meant to. Collected over water. So as soon as you see that it's collected over water, that's where you have to realize that this pressure right here, this 700 number, is the pressure of our gas plus the pressure from the water. Because even though the water is only at 20 degrees Celsius, some amount of it has turned into the gaseous state. So at this point, we're going to come over here and we're going to look up what the vapor pressure of water is at 20 degrees Celsius. And so the water is contributing this amount of pressure. Now, you know what? I made a boo-boo because this is okay. So this number right here is 17.5 millimeters of mercury. This is in kilopascals. Lauren, do I have a unit issue here?
Yeah.
Yeah, but here's the nice thing. I can actually convert between these units because I know that this number of millimeters of mercury is equal to this number of kilopascals. So I didn't do this intentionally. I just, again, not enough coffee. So I'm going to take this 17.5 millimeters of mercury, and I'm going to realize that for every 760 millimeters of mercury, because 760 millimeters of mercury, and we want to be in kilopascals, so that's going to be 101.3 kilopascals. So we're going to do a little bit of math real quick. I'm going to pop open my calculator here, and we're almost done, guys. 17.5 times 101.3 divided by 760. So I'm getting that this is 2.33. Is that right?
That's what I got.
Okay. So we're going to go with 2.33 kilopascals. So all of this is because of this silly fact that water is messing up our pressure. So the actual pressure that we want to use is not the 700. We're going to go ahead and subtract out the 2.33, and that's going to give me 697.67. So I've got a P1, a T1, and a V1. And now we say, well, what's the second set of conditions? It's STP. So we're trying to find volume. So the volume at the end is unknown. Standard temperature is going to be 0 degrees Celsius, which we know is 273 Kelvin. And then we're going to say that standard pressure is 1 atmosphere, but because we're using kilopascals, we're going to do 101.3 because that's the pressure of 1 atmosphere. Almost finished. Now at this point, we're going to go ahead and use the fact that we're doing the combined gas law. Didn't say anything about ends. And if I want to get VF by itself, I'm just going to do some algebra. So PI times VI over TI. I'm going to multiply the TF over, and I'm going to divide the PF over. That would leave VF by itself. And now I'm not going to write the units, but since everything matches up, I've got Kelvin, I've got Kelvin, I've got kilopascals, I've got kilopascals. If this is in milliliters, I'm going to get an answer in milliliters. So number-wise, 697.67 times 400 times 273. Sorry about that. Divided by 293, and PF is 101.3. So a lot of thinking, a lot of math, a lot of places where you can make silly mistakes. So it's common to see errors in these types of problems. But what you want to work at is just being careful. And I'm not sure I typed that in my calculator right. 697.67 times 400 times 273 divided by 293 divided by 101.3. No, I guess so. So what is that volume-wise? The volume I got is 2,566.8 milliliters. And it is completely possible that I goofed up my math there, unless somebody else wants to say that I'm on the right track. I'm going.
That's what I got.
Yeah.
Okay. All right, cool. So not the most exciting of things. I will do some more exciting stuff next week. But with that, I'm going to go ahead and stop recording. I'm going to stop sharing the screen in just a second. Questions, concerns, problems?